This is a walkthrough of Problem 4 on Exam 2 in Module 2 on page 50 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 4 is two non-conducting thin plates each have a net charge of plus 3 nanocoulombs uniformly distributed throughout their volume. Each plate is a 40 centimeter by 40 centimeter square with a thickness of 1 millimeter. They are face to face, 1 centimeter apart, as shown in the figure from the side. What is the field just outside the top plate? What is the field between the plates? A good diagram is essential to good problem solving. We have a good diagram right there, but it's not the scale. If this length is 40 centimeters, the height is supposed to be 1 millimeter, which is 1/400th of 40 centimeters. So a better figure to scale anyway is something like this. There's the top plate and there's the bottom plate. Very close together, very thin. It's going to be hard to draw positive charges on these two plates and put Gaussian surfaces in there, but it's a good idea to have both figures. So let's keep both. This is what it really looks like, and this will help us solve the problem. We also have to keep in mind that these are 40 centimeter by 40 centimeter plates. They look like lines when you look at them on the edge, but they are big plates. There's the relative scale. Next, we have to choose a good Gaussian surface for part A, which is up here. So we match the geometry of the problem, and we put the Gaussian surface through the point where we want to measure the field. Like that. Gauss's law is E dot A, and E is at the surface. So it's important, if you want to get the E field here, is to put the Gaussian surface there, right there. We want to know the field here, let's put the Gaussian surface through there. The field up here has to be the same as the field down here due to symmetry. And we know the field lines are directly away from the plate at the top and directly away from the bottom at the bottom. If I stick a proton right here, it's going to accelerate upwards. If I stick a proton down here at the bottom of the Gaussian surface, it's going to accelerate downwards. So we know that the field lines are at right angles to the Gaussian surface, so we know E dot A is the same as E times A. Gauss's law, E dot A is 4 pi kq enclosed. The combined surface area of the top and bottom, the top Gaussian surface, remember, it's 40 centimeters by 40 centimeters, 0.4 meters times 0.4 meters. It's hard to see in this diagram because it's showing it from the side, which is 0.16 square meters. And there's one of those for the top, one of those for the bottom, which is a total of 0.32 square meters, 2 times 0.4 meters by 0.4 meters. The area enclosed by the Gaussian surface, there's 3 nanocoulombs on each one of these, so that's 6 nanocoulombs. We can substitute in all the numbers. That's the E field at the top and bottom. There's the area of the top and bottom, and there's Q enclosed with everything in SI units. Solving for E, I get 2120 newtons per coulomb. So the electric field up here is 2120 newtons per coulomb, and it's directly away from the plate. That's the answer to part A. On to part B, which asks for the electric field between the plates, right there. What's a good Gaussian surface? Well, it should go through that point, something like this. Now we have a different Q enclosed. The E field at the top is different from the E field at the bottom, but Gauss's law is the same. E dot A is 4 pi kq enclosed for the entire Gaussian surface. We don't have symmetry that we did before. We can't say that the E field at the top is the E field at the bottom because there's another plate down here. We have to separate them. So we write E top times A top plus E top times E bot times A bot. It's E dot A for the top surface plus E dot A for the bottom surface. Before, E top and E bottom were the same, so we just factored them out, and we just added these two things. We know what E dot A is for the top surface, we just calculated it. We know the field up here is 2120. If we multiply by the area, we get E dot A for the top surface, 339 Newton meters squared per coulomb. We know that the area of the bottom plate, bottom surface, the bottom Gaussian surface, is 0.16 square meters. We know that Q enclosed is 3 nanocoulombs because we have just the top plate inside our Gaussian surface. The only unknown is the E field at the bottom. That's what the question asks for. There's the Gauss's law, E dot A for the top surface, E dot A for the bottom surface. Calculating this side, punching the numbers, we get 339 Newton meters squared per coulomb squared. So now the equation is E dot A for the top surface is that. There's E bottom times A, and here's 4 pi k Q enclosed. We can subtract 339 Newton meters squared per coulomb from both sides, and we get that E bottom must be 0. There's no field between the plates. And that's the answer to part B. And if you're just interested in getting answers, you're done. But as a physics student, you should say, what the heck? Why is it 0 in there? Does it make sense? I want to understand. Let's think. How can we figure this out? Let's look at one of the plates by itself. Let's simplify and say, what if there was one plate there? What do the field lines look like for this plate? It's an isolated plate. If I stick a positive charge up here, it's going straight up. If I put a positive charge down here, it's going straight down. The field lines are directly away from the plate, like that. What is the field out here for just one plate? It's got 3 nanocoulombs on it, uniformly distributed throughout the volume. What is the field out here? We can calculate it with Gauss's law. What surface should we use? There's a good one. Field lines going through the bottom, field lines going through the top. E dot A is 4 pi k Q enclosed. The total area is 0.32 square meters, one for the top, one for the bottom. Q enclosed, 3 nanocoulombs. We can solve for E, and we get 1060. So one of the plates has a field of 1060 newtons per coulomb at the top, going up, 1060 newtons per coulomb at the bottom, going down. Now, let's put the second plate in there. We're just going to bring it in and put it underneath. It's exactly the same. It's a non-conducting plate, exactly the same shape, exactly the same charge. There it is. Each plate produces an electric field of 1060 newtons per coulomb directly away from it. Up at the top, down at the bottom. Above the plate, up here, above the top plate, the fields are in the same direction. The total field up here is 2 times 1060. There's 2 contributions. Each one's 1060. That's 2120, and that's the answer we got for part A. The field just outside the top plate. In between the plates, the top plate is producing a field that goes down. The bottom plate is producing a field that goes up. And they're both 1060. They cancel. It's got to be 0. There can't be any field between the plates. It makes sense. Are we done? I don't think so. What's up with the fact that the plates are non-conducting? Why are they non-conducting? Would the answers be different? They would not be. The answers to part B are exactly the same, whether the plates are conducting or not. The field outside the plate is the same. The field between the plate is the same. But the charge distributions will be different, so let's consider that. With conductors, the charges are free to move. Like charges repel. If they're free to move, they want to get as far away from each other as possible. So they're going to appear at the top of the top plate and the bottom of the bottom plate. So there's the positive charges as far away from each other as they can possibly get. And there are the field lines. Field lines, there's no field between the plates. We can calculate the field above the plate if it's conducting. Same thing. The charge enclosed is still 3 nanocoulombs, but we know E bottom is 0. There's no field up here. All the field is at the top. So only going to have one area. So E at the top is 0.16 square meters, 4 pi kq enclosed. Seems straightforward. We can calculate E top is 2120. Same answer we got for part A. Are we done? Let's add part C. How about this? What is the electric field at the geometric center of the bottom plate? Right there, in the very center of the bottom plate. How do we get that? We can do it two ways. We can superimpose the fields from both plates, or we can use Gauss's law. Which one should we do? And the answer is do both. Let's do superposition first. So now we're going to bring the fields in and ask ourselves, what's the field at the center of the bottom plate produced by the top plate? And the answer is 1060. Straight down. This top plate makes a field of 1060 above, 1060 below, and we're below. So the field right here from the top plate is 1060 newtons per coulomb down. The field here produced by the bottom plate is 0. If you put a positive charge in the middle of the bottom plate and asked which way does the bottom plate push it, it doesn't push it in any direction, it's in the middle. So the field at the geometric center of the bottom plate is 1060 from the top plate, 0 from the bottom plate, so it's 1060 downwards. Now let's see if we can get that same answer using Gauss's law. Where should our Gaussian surface be? Well, it's got to go through the middle of the bottom plate. How about that one? We know what the field is up here. It's 2120. We want to know what the field is down here. E dot A is 4 pi kq enclosed. We only got one move for this chapter. That's our only move. The trick is to pick a good Gaussian surface. Again, we have to split the top and the bottom because the field's not the same. So we write E top dot A top plus E bottom dot A bottom is 4 pi kq enclosed. We know what E dot A is for the top surface. We know the area. We know the field. The field's 2120. The area is 0.16. We can get that. We got it before. 339 newton meters squared per coulomb squared. But what is Q enclosed? How much charge do we have inside our Gaussian surface? Each plate is 0.3 nanocoulombs. The plates are non-conducting, and the charge is uniformly distributed throughout their volume. The plates want to move, but they can't. It's non-conducting. They're immobile. The Gaussian surface encloses all of the top plate and half of the bottom plate. What do you think the charge enclosed is? Well, it's the charge on the top plate plus half the charge on the bottom plate, 4.5 nanocoulombs. So there's our Gauss's law equation. E top dot A top, we got that already. There's our unknown, 4 pi k Q enclosed, 4.5 nanocoulombs. We can calculate this side, punching those numbers, and we get 508 newton meters squared per coulomb squared. We want to solve for E bottom. We subtract 339 newton meters squared per coulomb from both sides, and we get E bottom times the area, 0.16 square meters, is 169 newton meters squared per coulomb squared. Solving for E bottom, we get 1060, which is the same answer we got by superimposing the fields. Are we done? I don't think so. There's a lot of ways to calculate the field in the middle of the bottom plate. Do this. How about that surface? How about that Gaussian surface? It goes through the middle of both plates. Can you calculate the field right here? How much charge is enclosed in your Gaussian surface? Here we don't know what E top is. We want to solve E bottom, but we know they're the same. And we know what their area is. Are we done? I don't think so. How about this one? Let's go through the area between the plates and then straight through the bottom plate. Every single one of these Gaussian surfaces should give 1060 newtons per coulomb downward for the electric field at the center, geometric center of the bottom plate. Are we done? Okay, we're done.